So endothermic takes in energy. Basically, it needs energy, right? So cold pack would be an example. What's exothermic? Yeah. Like combustion, what does it do? Gives off heat, okay? It's combustion reactions. Give me an example of exothermic. Those are easy. There's lots, right? Volcano, sure. What else? Yep, sure. Giving off energy. Barbecues, yes. Okay. Stoves, etc. gives off energy, right? Okay. So that's kind of the difference between those two. Okay. Let me ask you these here. So, melting of ice. What would that be? Endothermic or exothermic? Is energy going to be required for us to melt the ice, or does it give off energy as ice is melting? Does it take in energy, or does it give off energy? Does ice cubes release energy? They take in energy, don't they? So endothermic, yes. Okay. Photosynthesis, that's a tricky one, perhaps. Well, maybe not. You guys probably should know that, eh? Photosynthesis? Plants? Photosynthesis. Takes in energy or gives off energy? Endothermic or exothermic? Endo takes in, exo gives off. What do you think? Sure. Endothermic, yes. Where does the energy come from? The sun. Yeah. So that would be endothermic as well, yes? Endothermic. Energy from the sun is absorbed or required. Respiration. Respiration. It's the opposite of photosynthesis. So there you go. Yeah. Exothermic. Okay. So respiration would be the opposite. So of course, exothermic. Okay. Reaction that occurs inside a car engine takes in energy or releases energy? I don't know. Sure, go ahead. Exothermic, right? And we are combusting fuel, yes, basically. And you know when you were driving in the, especially nowadays and in the wintertime, yes, you see smoke come out of the exhaust pipe, which is not really smoke, hopefully, right? That is more likely what? Steam, right? Water vapor, okay, as a product of exothermic, H2O, steam, okay? Charging a battery takes in energy or releases energy? Charging a battery, yeah. Probably endothermic, takes in, right? Okay. So those are some examples of endothermic or exothermic, okay? Combustion reactions, which we're going to talk about this year, are exothermic. They give off energy. Sometimes to make compounds, they take in energy, right? Okay. So today, we're going to identify and classify chemical changes. And let me move this down here. Oops. And write word and balanced chemical equations for significant chemical reaction. Translate word equations into balanced chemical equations and vice versa. Okay. So when we look at representing a chemical equation, okay, a chemical reaction occurs when one or more substances change to form different substances. A chemical reaction can be represented with a word equation. And for example, here's a reaction for photosynthesis. Water and carbon dioxide gives us oxygen and glucose. That should be an arrow there, by the way. Okay, like so. Okay, so once again, we can write this out as a word equation, or we can write it out with the actual compounds, which we're also going to do today. So what are the reactants, for example? Well, like I said, water and carbon dioxide would be the reactants, right? The reactants are on the left-hand side of the equation. When I combine water and carbon dioxide, and of course some energy, okay, we get some oxygen and glucose. I should make that better. And glucose. Okay? So that's an example of a word equation. Of course, the reactants are on the left-hand side, products are on the right-hand side, yes? Okay, so reactants versus products, all right? So, word equations, those are fine. Most of the time, though, we probably want to use actual chemical compounds and write out that actual compound and what it looks like, okay? So, let's do this right here. I'm going to actually cross this out for a second here, okay? In a chemical equation, the compounds are represented by their chemical formula, okay? Here's the chemical equation for this. So water, we said, water and carbon dioxide, CO2 gas. So those are the reactants, of course, right? Those two things react together, water and carbon dioxide, and they will form oxygen, O2. Oxygen comes in twos, don't forget. And glucose, which is C6H12O6, okay, like so. All right. And I guess I should probably put the state for that one solid. Okay. So an equation represents, like I said, the compounds that we're actually going to use there. Okay. So that would be a chemical equation. Now, what we're going to get to eventually today is, of course, we should probably balance the chemical equation as well, right? We should make sure that we have the same amount on both sides. So we're going to get to that today, of course. But that would be just a quick little example. We're going to get to that part in a second here. The subscript of L, of course, indicates that we have a liquid, okay? Or G is a gas and S is a solid. AQ represents aqueous. That means we've put it into water, okay? So you might have to go to the periodic table to determine the states of elements. Now, your periodic table is not colored, okay? I don't think, right? No, it's not. But over there, you can always use that one as well, okay? Now, this is not the end of the world for you guys. In Chem 20, we'd probably ask you a little bit more, but you know, for right now, it's not the end of the world, but you have that available to you as well, okay? So anything in gray writing there, guys, is a solid. Okay, so look at all the metals there left of the staircase. Pretty much all of them are metals, except for mercury, right? That's a liquid. Blue is liquid. That's mercury, and Br, which is bromine. Those are the only two liquids. Anything in red lettering is a gas. Okay, like hydrogen's a gas, nitrogen's a gas, oxygen's a gas, fluorine, chlorine, and then, of course, the noble gases are gases, okay? So gray is, like I said, solids. Blue is the two liquids there, and the rest, the red, are the gases, okay? If you're doing these at home and you're not sure, you can always jump online and Google it, kind of thing. And there's even a periodic, the same periodic table that we use on yours is also available online, okay? So, and it's colored and everything else for you there, okay? So, all ionic compounds will be solids at room temperature unless they are dissolved into water. Remember, ionic compounds, one of the properties of ionic compounds is that they hold together really well, don't they? Plus, minus, what's that structure called? Yep, crystal lattice. So plus, minus, plus, minus, plus, minus, plus, minus hold together really well. That is a solid. When you take that solid and you put it into water, well, what happened yesterday, guys? What happened to the blue one yesterday? It dissolved, right? So we call that AQ, right? Aqueous. We just did a whole lesson on that. Solid AQ, solid AQ, solid AQ, right? So there you go, okay? Information about molecular compounds will be provided because molecular compounds have a wide variety of states, okay? Water is a liquid. CH4 would be a gas. And then we got sugar, which is C12H22O11, and that's a sugar, that's a solid, okay? So there's a wide variety of that there, okay? Now, law of conservation of mass, okay? We have to follow law of conservation of mass, and basically what that says is that the total mass of the reactants has to equal the total mass of the products, okay? So the reactants have to equal the products. They need to be balanced out, okay? Matter cannot be created or destroyed, and the total number of atoms before the reaction has to equal the total number of atoms after the reaction, okay? We're not going to do that, but let's do this. H2O2, let's just do this part right here. So, I guess I should use states. Let's copy this one out here, guys. Okay. So, how do we make water in this case here? How do we make water? Well, we take some hydrogen. Hydrogen comes in twos, okay? Hydrogen comes in twos. We take some oxygens. Oxygen comes in twos, okay? How do we make H2O? All right, so look, we'll act it out. How's that? Okay, so look, if we want to make water, H2O, this is, where are we here? That's water, okay? Yes, H2, and that's your O there. So that's water, it actually looks like that, it's polar, right, et cetera, et cetera. So how are we going to make this? Well, we need to make that, we need to take two hydrogens, okay? So here's my two hydrogens, see, H2, yes, there's H2, and we need two O's. And the O's actually have, by the way, let's see here. Let me pick a different one. There we go. Okay. Now, the O is actually double bonded to itself here. So it looks like that. So this is what H2 looks like right here, H2, and O2, okay? Now, if I want to combine these two together to make H2O, how is that going to happen if I just have these two here? Well, first thing that could happen is, of course, we're going to put them together. They might require some energy for them to actually react together. So there has to be collisions, and there has to be a certain amount of energy with those collisions to reorganize them, okay? And what you have to understand is when we're balancing chemical equations, it's not addition, okay? It is not addition, right? So we might take one thing and three things. That doesn't necessarily give us four things. It's like taking a sandwich and some ham, and you mix them together, and what do you end up with? No, wait, that's wrong. Never mind. You take some bread, that's what I meant to say, and some ham. If you take some bread, two pieces of bread, and some ham, and you put it together, what do you get? A sandwich, right? You don't get three things, you get a sandwich. Okay, so you're recombining it together, you're not adding them. Okay, so listen, if I take H2 and O2, how am I going to make H2O? Well, look, I'm going to break some bonds, okay, and I'm going to reorganize them. So look, H2 and O goes together. Yes? What about this one? What does it still need? Because I had two O's to start with, right? What about this one? It needs what? Two hydrogens, doesn't it? Okay. So I guess maybe I should have started with maybe 4 hydrogens altogether, right? And 2 of these, yeah? So maybe what, like I said, going back to this here, let's go back here for a second. Let's do this. And let's do, and then we'll just put this together here. Just give me 1 second here. All right. Okay. So the point is Maybe you need 2 of these, yes, to go with 1 of those, right? So 2 O's here and 2 of these to start with to make, how many would you make over here then? So if you took these 4 hydrogens and we put 1 on here, for example, and 1 on here, okay, there's a water for you, and there is another water here, yes? Okay, so you're actually making 2 waters from those, yes? So you might want to consider, hey, I can make 2 waters if I use 2 hydrogens, yes? Okay, 2 sets of those. So look, how many hydrogens do you have altogether? How many did we use? 4. How many hydrogens do you have here? 4, yes? Okay. How many O's do you have here? 2. How many O's do I have here? 2. Okay. So that's what we need to look at today. We need to look at how we're going to rearrange these things, making sure we have enough on both sides. And I'll give you some tips for that as we go through those. Okay. So when you're going to write a balanced chemical equation, to write a balanced chemical equation, start with the chemical equation and add coefficients in front of the products and reactants. Each atom should appear the same number of times on the reactants as it does on the product, so make sure you have the same number on the reactant side as the product side, of course. Okay. Let's take a look at this one here. So let me just get rid of this for a second. So let's take some copper. You guys can write this one down. And silver nitrate. Okay. Copper and silver nitrate. Have you guys ever done reaction types in grade 9? Yes, no? Reaction types? Like single replacement, formation, decomposition? No? So this is going to be brand new for you. Okay, there we go. All right, so we're going to look at how do we write these equations, okay? So this would be actually called here, and if you want to write this below, you can. It doesn't matter really where. This is copper, and we would react that, and silver nitrate, right? Silver nitrate. Now, this is a special type of reaction. This is called a single replacement, and we'll get to that in the next few days here coming up, okay? So what happens is the metal parts will switch, and for today I'm going to give you this because we just need to worry about balancing. So the copper and the silver would switch places, and we're going to get silver by itself and copper nitrate, and it actually forms that one there. Okay, so it would look like that. I'm going to give you that balanced chemical equation today. Okay, we'll worry about writing these out. Eventually you're going to write these out on your own. All right. Yeah. Yeah. Now, if we're going to balance this chemical equation, let's start. There's a couple different ways you can do it, guys. I like to do left to right, like we read a book. Take one element at a time, okay? Or kind of group them together if you can. How many coppers do we have? 1. How many coppers do I have over here? 1. Okay? 1. The 2 only goes to the stuff in the brackets, right? Okay? So I got 1 copper, 1 copper, right? Good? So we're going to leave them alone. Don't touch them because they're balanced. I got 1 silver, Ag. Yes? How many Ags do I have here? 1. So that's good too, yes? Okay. Now, you could try to balance these each element by each element, but I would caution you on that in some cases. Anytime you talk about ionic compounds involve what? This is going to be kind of maybe a silly question, but ionic compounds are made up of what two parts? Yep. Metal and a non-metal, okay? So there's the metal, and there's your corresponding metal there kind of thing, right? This would be your non-metal, yes? NO3 1 minus, correct? Nitrate. There's your non-metal here, nitrate, same thing. See how they're kind of grouped together? Okay, so look, how many nitrates do you have over here? 2, yes? So when I come back over to here, how many of these do I want? 2. Where do I put the 2? Can I put it just over here like this? No. You got to put it in front, all right? It has to be what we call the coefficient in front of the compound, okay? Here's the problem. Is everything else still balanced? No. What do I need to fix? How many silvers do I have? So now I need to come back over to here and put a 2 there, okay? What you should do is when you think you're done, you should probably double check, yes? Copper, 1, pay attention. 1 copper, yes? 2 silvers, 2 silvers. 2 NO3s, 2 NO3s. I think everything's good now, yes? Okay? If you want to be specific on atoms, if you want to double check the number of atoms for each one, you can do that now, but I wouldn't do that when you're balancing because it gets kind of tricky sometimes. So 2 AGs, 2 AGs, 2 Ns, there's 2 Ns, yes? 6 O's and 6 O's, right? If you want another version of this, look, copper and AgNO3, watch this, AgNO3, I need 2 of those apparently, okay, to give me Ag and Ag and copper NO3 2, okay? Do you have the same number of stuff on both sides if you entirely wrote that out, right? Look, copper, copper, yes? Okay. Ag, there's 2 of them here. There's 2 of them there, right? 2 Ags, 2 Ags. NO3, there's 2. There's 2 NO3s there, okay? So it looks like everything works out, yes? Okay. So that's something we need to keep in mind, all right? Let's do a few more here. There's a lot of rules here for that. And I think I'm just going to go through this with you here and balance a few with you. Look, guys, if it's an ionic compound, we want to kind of balance based on ions, okay? Metals versus non-metals kind of thing, yeah. Yeah. Good. Yeah, and we'll get to that. You won't know that yet, but it forms the one that is first on the periodic table usually. Usually, okay? You're going to have to wait until we do the next lesson, which is where you make your own equations, okay? Today, I'm going to give you something like this, okay? So let's work on this one together here. Iron 2 nitrate and sodium phosphate gives me, so those are my reactants, is going to give me sodium nitrate and iron 2 phosphate, okay? Now this one's specific with the iron 2 here, so that there. So go ahead and write that down. Write that down, guys. Iron 2 nitrate and sodium phosphate will give me sodium nitrate and iron 2 phosphate. Iron 2 nitrate and sodium phosphate. Okay. So listen, this is going to be incredibly difficult if we cannot do ionic compounds, writing formulas, yes? Or molecular, whatever the case might be. Because if I give you this and you don't know what iron 2 nitrate looks like, we're probably not going to balance it properly. Okay? We're not going to be able to write out a chemical equation for this. We're not going to be able to do a lot of things. So I can't stress that enough. If you're still not sure about ionic compounds and molecular compounds, you know, your last quiz wasn't so hot, you probably should come see me so we can do some practice. Okay? And I'll give you some to practice, and then I'll check them over. I'll give you some more, et cetera, et cetera. Okay? All right? Now is a good time. We could figure this out here. Iron 2 nitrate. Let's see. Iron 2, which means it's a 2 plus, right? Nitrate. So once again, you look that up in the top left. Should look like this, yes? 2 plus, 1 minus. Yes? 2 comes over and down, brackets, right? 1 comes over and down, we don't write it. Okay? Good so far? Now, this is on a compound, and usually ionic compounds are solids unless we place them into water. This would be a case where we put it into water. Okay? So we're going to put a little AQ behind here, like so. Means I put it into water. Okay? And once again, you don't need to really worry about that too much for today. Okay? Sodium phosphate. Okay? Sodium is a 1 plus. Phosphate, top left. 3 minus. 1 comes over and down. Yes. 3 minus, over and down. Okay? So that's what sodium phosphate should look like. Okay? And like I said, if you're not sure what I'm doing here, if you can't figure that out, you better come see me, because this is what we're going to be doing for the next little bit here, guys. And it ain't going to get easier unless we know how to write out those compounds. Okay? So if I mix these two compounds together, okay, it says I get sodium nitrate. Sodium is a 1 plus. Nitrate is a 1 minus. So 1 plus, 1 minus, swap and drop. We don't write ones, right? 1, 1. And that'll be aqueous again here. Once again, we'll explain that in a bit. And we get some iron 2 phosphate. Iron 2 phosphate. Now, let me move this up here. Iron is a 2 plus. Phosphate is a 3 minus. Okay? So the 2 has to come over and down. I will need to put brackets here. 2. The 3 is going to come over and down, and I'll put a 3 there. Okay? Question so far? Actually, you guys could know, you would know this. How do I know what these states are? Usually when we talk about ionic compounds, we take aqueous and aqueous and we mix them together. So we take 2 water solutions, mix them together, and you could look this up on the solubility chart and you would see that this is aqueous. This is very soluble. This one is not very soluble. So we actually will put an S here, like so. So you'll actually get a solid that's being formed. Okay? So you get that's called a precipitate. Okay, solid. So if you look at phosphate across the top on your solubility chart, and you find iron 2, okay? Iron 2 won't be here, it's going to be down in here. Okay? So not very soluble. Okay? Now, we need to be able to do that. Okay? And that's going to maybe takes a little bit of practice, but once again, if you don't know what these ionic compounds look like, it's going to be pretty tough. Balancing is going to be incredibly tough because it's probably not going to match up particularly well. So it's going to be even tougher to do that. Okay, so I strongly encourage, come and see me, let me help you before it gets too late here. Okay, now we have to balance based on atoms / ions. Okay, look, ionic compound, ionic compound, ionic compound, ionic compound. Yes, we have to know that. Metal, non-metal, positive, negative, positive, negative, positive, negative, positive, negative. You will balance this based on positives and negatives, okay? In other words, you'll balance this based on the metals and the non-metal negative ions. So watch, Fe. One Fe here, correct? Yes? This 2 only goes to stuff in the brackets, guys, so there's one Fe. How many Fe's do I have over there? On the right side. How many Fe's do I have on the right-hand side? Yep, 3. I only have 1 here, yes? So I should probably fix that by putting a 3 here, yes? You can only put numbers in front now to balance the chemical equation. Okay, that's the coefficient. So 3 Fe's, 3 Fe's, yes? Good. How many NO3s do I have? So I'm going to look, this is the positive part, this is all the negative part. How many NO3s do I have on this side here? Do I have any over there? No. Okay, just right here. How many do I have? This is where you got to be careful. How many do you have in total? No, there's more than that. 6, yes? Look, I have 3 of these, right? Or 3 times 2 is 6 of those. If I wrote this out 3 times, I'd have 2, 4, 6. Yes? 3 times 2, 6. How many NO3s do I have on the right-hand side? At this current time, I have, no. How many NO3s? NO3s altogether, how many do I have? 1. Right? Look, NO3, I have 6 NO3s. I have 1 here. Yes? So I'm going to put a 6 in front. Okay, look, I'll do it again here. Watch. 6 NO3s, yes? 3 times 2, 6 of those. I now have 6 of those, yes? Okay? Now, I'm going left to right like a book, guys. How many NAs do I have here? No. 3, yes? There's a 3 behind it, guys. Na3. There's 3 NAs. How many do I have? How many NAs do I have here? 6. So how am I going to fix that? Well, if I got 3 NAs, what number can I put in front to make 6? 2. 3 times 2 is 6 NAs. Yes, just went. And how many PO4s do I have right here, guys? Right here. How many PO4s do I have in total now? 2, right? Look. 2 PO4s, yes? How many do I have here? 2. We're at the end now, right? Aren't we? I think we're done. Let's double check real quick. 3 FEs. 3 FEs. Yes? 6 NO3s. 6 NO3s. 6 NAs. 6 NAs. 2 PO4s. 2 PO4s. Should be good. Okay? If you want to, see, the reason you don't want to balance based on, I'll tell you, if you want to balance based on each atom by itself, that's not a good idea in this case. And I'll tell you why. Because look, you'd have to, there's O's right here. In fact, there's 6 right here according to this. Well, there's actually more, yes? But you'd have to balance these O's with these O's, and that's just on this side, with O's and O's on that side. How many possible combinations would there be? You know what I'm saying? Like, do I put 2 in front of this and 3 over here and 4 there and 5 there? Or do I put 3 there and 2 there and 5 and 4 there? Or what are, like, there's literally probably about a million combinations you could do just to balance O's, okay? So normally, you know, if you can balance each atom by itself, absolutely. But with ions, ionic compounds, you want to balance based on ions, okay? Metals to metals, non-metals to non-metals. Trust me, okay? Yeah, go ahead and ask now. Yep. Well, because look, this right here is 1 NO3, right? There's not 3 of them. There's only 1. Because NO3 is all together. So that's all 1. So right now, I have 1 of those, right? Here, don't forget, I already have 2, right? 2 of all this, right? Now I started balancing based on the iron, so I had to put a 3 there. So now I have 3 and 2, 6 of NO3. But here, remember, I still just have 1 here. So I can't put a 6 here because I can't change it once I've done the swap and drop thing. So I had to put the 6 here to get to there, which means 6 NAs. This one was from swap and drop. So I already had 3 there. The only way to help to fix that is to put the 2 there to get the 6 Na. Okay? So part of that comes from the swap and drop part. Okay? All right, let's look at another one. Okay, let's take a look at this here. I'm going to rewrite this here, guys. You know what? I'm going to do it a little different. I'm going to write it like this, so don't worry about that. Okay. Yeah. Let's write down this example here. This one I could give you as a word one as well. Okay, we could totally do this as a word one as well. I'll tell you what it would look like. Okay, but just to save, not save some time, but because you'll get some of these, of course, as well. Does anybody know what kind of reaction this is, by the way? Nope. That's not what we call it, but there is oxygen involved. Combustion. Okay. Anything plus oxygen is a combustion reaction, technically. Okay. This would be methane gas, which we would call carbon tetrahydride. Yes. Okay. So we could do a word equation as well, fairly easily. Carbon tetrahydride plus oxygen, O2, carbon dioxide, water, okay, or dihydrogen monoxide, or water, okay? Now, this one, is this ionic compounds here, guys? Are these ionic compounds? No, okay? So now, listen, they're not ionic compounds. We cannot balance based on ions, okay? Guys, pay attention. We cannot balance based on ions. We have to balance on each atom by itself. Okay, so look. Here we go. This might be easier for you. I don't know. Let's take a look. We got to start left to right. Okay, so we don't skip anything. You don't have to. If you get really good at this, or this is easy, no worries. Start wherever you want. Okay. You know, I've done a couple of these, so I kind of like, I know which one. I know where to start, kind of thing. But if you're starting out and you're not sure, you start left to right, like you're reading a book, okay? We've all done that. Carbon, carbon. Balanced? Yes or no? Okay, leave it alone. H4, so 4 hydrogens. How many hydrogens I got over there? 2. How am I going to make 4? Times it by 2, right? Put a 2 in front of it. We can't change anything else, remember. We got to put numbers in front. So I'm going to put a 2 here. Okay, is that 4 hydrogens now? Okay? And if you want, you can do the same thing I'm doing. You can kind of check them off as you go. It's up to you. You don't have to. Okay? I would say after a while, we probably shouldn't underline everything, and but if you want to kind of keep track, that's fine. Okay. Okay. How many oxygens do I have here? So this is balanced. This is balanced. Yes. Right. So we're good so far. How many oxygens I got? 2. Okay. So I got 2 here. How many do I have here? 2. And how many do I have here? Okay. So actually, here I got 2, and here I got 2. So that's a total of 4 on the product side, right? 4. But I only have 2 here. So how am I going to fix that? Times this one by 2. 4 O's, yes, 4 O's, 2 and 2, 4 O's. Good? That's it. Okay, that's not so bad, eh? Okay. Like I said, take one at a time, right? Double check when you're done, make sure. But 4 O's, remember, this is kind of like the left versus right? Reactants versus products, right? So 4 O's here, 2 there, and 2 there, that's 4 there, okay? So that's how I got to fix that. Let's take another one here. Okay, we need an arrow there, okay? Okay, here we go. Okay, write that out first, guys. Sodium chloride gives me sodium and chlorine, okay? Sodium chloride gives me sodium and chlorine. Sodium chloride, write that out first, breaks down into sodium and chlorine. Okay? Now, what does sodium chloride look like? Okay, once again, just take one part at a time. We need to come up with a chemical equation for this, yes? Sodium chloride, right? What kind of compound is this, by the way? Ionic. So 1 plus, 1 minus, yes? 1 plus, 1 minus, swap and drop, we don't write the ones, right? Okay? What state should I use with sodium chloride? Now, here's kind of like, this is going to be part of it over the next few days here, guys. What state do I want to use? And the answer is, well, it depends on the type of reaction you're doing, okay? This is obviously an ionic compound, okay? Am I mixing with another ionic compound? No. I'm just taking sodium chloride, and what am I actually doing here? I'm making sodium and chlorine, okay? This is actually called, do you know what this is? Oh, well, it is, but what am I actually doing here? I'm taking an ionic compound and I'm breaking it down into its elements. What would we call that, do you think? Any idea? No? How about this? Decomposition. So we are decomposing sodium chloride into its elements, basically. Okay? To do this, we would probably need lots of heat. Ionic compounds tend to require lots of heat, probably upwards of 1200 Celsius, 1600 Celsius. So this is a solid, okay? And when I basically heat this up, at some point, I will get back the elements that I used to make this compound from. So this is the key here, guys. Sodium chloride involves ions. To make this, I had to use elements, okay? So sodium is a solid. You can look over there. It's in gray. Okay. Chlorine, look where chlorine is there. It is a gas, but here's the kicker. What does that mean? Other than you're like, yeah, that's true. Do you remember what happens with these ones? I have no brighter, clever friends, people stupid. They come in what? Pairs. Remember? I2, H2, N2, O2, F2, Cl2, Br2, P4, and S8. Yes? We call them what? What's the actual term we give those? Molecular. Oh, it's been a while apparently. Elements, yes? Molecular elements. I have no brighter, clever friends, people stupid. I2, H2, N2, O2. So you have to remember those. If you have an element, like chlorine or bromine or oxygen or hydrogen, remember when I did oxygen on the last one? It was O2, right? Or when we made water, H2, O2, right? H2O2, hydrogen and oxygen. So this comes in twos, guys, and it is a gas. Okay. Now, to balance this one, we're going to go left to right. So, look, sodium, yes, we're good, right? So far. 1 Cl here, 2 here, yes? So how am I going to fix that? I got 2 there. I only got 1 here. I need to put a 2 here, don't I? Yes? So then what you got to remember, guys, is, okay, if I put a 2 here, doesn't that change this one now too? So now I got to make sure I go back and change this one as well to make sure that that's balanced. Okay? That's called a decomposition reaction. Basically means we're decomposing this compound back into its elements. Yep. No. All right. Questions, anyone? Okay. Do we want another one for practice, maybe? Let's see. I don't know if I have any more off the top. I can always make one, I guess. Let's see here. Okay. What about, let's see. Well, let's do this one. Oh, that's not a very good one, actually. That's all right. Okay, that's okay. Calcium and magnesium sulfate. Okay, calcium, magnesium sulfate. And that would give me, by the way, magnesium and calcium sulfate. This is not the best one to do in retrospect, but that's okay. Listen, so remember, okay, what we're kind of dealing here with. You always want to start out with, of course, writing out these elements, compounds, whatever, okay? Making sure we use charges where appropriate. You know, calcium. Calcium looks like this, guys. It is a solid, okay? Is there a charge on calcium? So should I put 2 plus up there? And the answer is no, okay? We're going to have to spend some time on that. If you notice any equation I've done today, there's been no charges at all, right? There hasn't been a 2 plus or a 3 plus or a 4 plus or a 2 minus, because ionic compounds, when you write them out, they're neutral, right? 2 plus, 2 minus, they cancel. This is just the element calcium, and I'm going to react that with some magnesium sulfate. Now, ionic compound, yes, magnesium sulfate. Magnesium is a 2 plus, but remember, sulfate is a 2 minus. So we will swap and drop and reduce. Okay, 2 plus, 2 minus, we'll leave it alone. 2, 2, but really it's 1 and 1, isn't it? Okay. Now, I'd have to look up the state of that one. I'm actually not sure. I'll double check that in a second here. Okay. Now, I'm going to get from this, when I react these two together, and actually this one might not actually do this, but just for practice sake, magnesium and calcium sulfate. Now, magnesium's by itself, so there's no charge on it, okay? And calcium is a 2 plus ionic compound, but that's a 2 minus. So swap, drop, and reduce, yes? This one for sure I know is a solid, and actually now that I know, this is actually going to be a solid as well, okay? And like I said, not a great one to do, because why? You don't really have to do anything, do you? Is it balanced already? You know, once again, Ca, 1 Ca, Ca, right? That's 1 and 1. 1 Mg, 1 Mg. SO4 we want to keep together because it is a 2 minus charge. SO4, 2 minus charge. So we're good, right? Balanced already. Sometimes they are balanced already, okay? Sometimes that happens. Sometimes they are not. So you have to be careful, okay? Okay, I think the best thing for you guys to do is to try some of these here. So I will stop this.